Welcome to my video course on railway safety and systems engineering. Today, we're diving into a truly fascinating and, honestly, absolutely critical topic, hazard identification, or HazID. When we talk about engineering for the railway, we're talking about massive, incredibly complex systems where the stakes are just sky high. The whole point of everything we do is to systematically uncover hidden dangers and stop accidents before they ever even get a chance to happen. So let's just jump right in and explore the actual engineering techniques we use to build a truly safe railway. To get us there, here is our game plan for today. First, what exactly is hazard identification? Second, the two phases of HazID. Third, empirical techniques, specifically using checklists. Fourth, preliminary hazard analysis. And finally, deductive methods, looking at brainstorming and HAZOP. Let's kick things off with Section 1. What is hazard identification? At its absolute core, HazID is the proactive, systematic process of finding conditions that could trigger an accident. But to accurately spot these hazards, you've got to comprehensively define three crucial areas. First, you need to understand the functions the system has to perform, like what is it actually built to do? Second, the users. Who is interacting with the system and how are they going to behave? And third, the technical interfaces with other systems. Think about dropping a brand new fire panel into an underground station. You can't just look at that panel in a bubble, right? You have to understand its alerting function, how a stressed out station operator might interact with it, and how it plugs into the station's wider electrical and telecommunication networks. It's all connected. Now, here is a massive point I need you to remember. A hazard is not the same thing as its cause. This is such a common trap engineers fall into, and it literally wastes so much design time and budget. Let's go back to our fire panel example. The function is to provide an alert. The hazard is a state, like no alert provided to the interfaces. That right there is the hazard itself. But why did it happen? Well, maybe there's a faulty power supply, but that faulty power supply is the cause, not the hazard. If you mix those two up, you're going to end up with an unmanageable mile-long list of components to track, instead of a tightly focused list of actual system vulnerabilities. Moving right along to Section 2, the two phases of HazID. A bulletproof hazard identification strategy really relies on two distinct phases. First up is the empirical phase. This is all about exploiting past experience. It looks backward. We're essentially looking at documented history and data reporting to ask, okay, what has gone wrong before on the railway, and how do we make sure it never happens again? But then we have the deductive phase. This is proactive forecasting. It looks forward into the complete unknown. It asks what completely novel things could go wrong in our new design that we haven't actually seen yet. To build a robust, fail-safe system, you absolutely have to use both approaches. Which brings us to Section 3, empirical techniques, specifically focusing on using checklists. I know, a checklist sounds super simple, right? But in systems engineering, it is a remarkably powerful empirical tool. It relies completely on documented historical data, failure analysis, and predefined lists of known issues. When an engineering team uses a formal checklist, they're basically downloading the collective past experiences, accident reports, and hard-learned lessons of the entire railway industry. It's a way to ensure that any previously encountered hazards are systematically addressed right there in the design phase. It guarantees we learn from the past and never ever repeat a known mistake. Next up, Section 4, Preliminary Hazard Analysis, or PHA. Preliminary hazard analysis is performed super early in a project's lifecycle, usually during the initial concept or system definition phase, way before any detailed designs even exist. The goal here isn't to get bogged down in tiny microchips or complex wiring diagrams. No, the goal is to pinpoint massive, high-level risks early on. By catching those overarching hazards at the concept stage, engineers can establish the initial Safety Requirements Specification. That specification becomes the bedrock, dictating the foundational safety architecture for the whole project moving forward. It ensures safety is baked in right from day one. But this brings up a really fascinating challenge, and I want you to think about this for a second. What if we are building a cutting-edge railway control system that has literally never existed before? We can't entirely rely on an empirical checklist, right? Because there's no exact historical data for technology that's brand new. You can't rely on past experience if the experience doesn't even exist yet. And that perfectly leads us to Section 5, deductive methods, looking at brainstorming and HAZOP. When history can't hand us all the answers, engineers have to rely on proactive forecasting using structured logic. Let's look at brainstorming first. Now, in a railway engineering context, this is a formal, deductive technique done in highly organized workshops. It is absolutely not just a bunch of people sitting around having a random chat. Instead, a panel of subject matter experts systematically goes through every single system function and user interaction to proactively hunt for potential deviations from the intended design. Let's break down how this logic actually flows step by step in a professional workshop. Step 1. The engineering team systematically considers every system function. They isolate exactly what the control system is supposed to achieve. Step 2. They analyze all user interactions. How does a signaler or a train driver actually engage with this system out there in the real world? And Step 3. They identify potential deviations. The experts actively look for ways the system might behave differently than intended, figuring out if each deviation represents a genuine hazard that requires mitigation. Now, if you need a method that's even more rigorous and structured than brainstorming, you turn to a HAZOP. That stands for Hazard and Operability Study. This is a highly formalized deductive technique. Instead of just throwing out open-ended what-if questions, a HAZOP uses very specific, predetermined guide words to intentionally spark conversations. It essentially forces the engineering team to evaluate exactly how a system function, a user operation, or a technical interface might deviate from its intended design in highly specific ways. To pull this off, a HAZOP relies on specific guide words like no or not, more, less, and reverse. So let's say our system function is simply to apply the brakes. The HAZOP facilitator injects a guide word into the discussion. Let's use no. Result? No brakes applied. Okay, that's a critical hazard. What about more? Well, that means more braking force than intended, which could cause passenger injuries. What about reverse? The system actually accelerates instead of braking. It's a real game changer. By forcing these specific guide words into the conversation, the HAZOP seamlessly creates these vital, rigorous evaluations of potential operational deviations that the team might have otherwise completely missed. So, as we wrap up this explainer, I want to leave you with a final provocative thought to chew on. How will you apply these empirical and deductive tools to build a comprehensive safety net in your next project? Remember, it's by combining those backward-looking lessons from historical checklists with the forward-looking rigor of deductive forecasting, like HAZOP, that you can ensure the absolute safety and integrity of the railway system. Thanks, we can see in next video.